2014 Level 3 Physics Waves Paper. Question 1. The sea organ. The sea organ in Zadar, Croatia is a musical instrument that creates its musical notes through the action of sea waves on a set of pipes that are located underneath the steps shown in the picture, which you can't see that picture. The sound from the pipes comes out through the regular slits in the vertical part of the top step. If we scroll down and have a little look, that'll make a bit more sense. So basically the seawater comes in and out here, driving air through the tube, and the organ pipe here creates a sound, a note according to the length of the pipe. In the same way that a reed would vibrate the air here, we've got the seawater vibrating the air. And I guess the sound comes out the top to the people standing on the steps listening. To produce a sound, carrying on here, the organ pipes must have air blown into them, so each organ pipe is connected to the top end of a tube as shown in the diagram, and as we've talked about, the action of the waves pushes water, we saw about that too, creating a flow of air on the upper end of the tube. The diagram on the right shows the inside of an organ pipe. These organ pipes have one closed end. Okay, so there's the closed end just down here. Calculate the length L of an organ pipe with one closed end, there's our one closed end, that produces a fundamental standing wave length of 2.60 meters. Okay, when you've got a diagram like this, draw the fundamental in it. We must have a node at this end. We must have an antinode at this end because it's open at the antinode end and closed there. So we're going to have approximate shape, approximate because I'm not very good at drawing on this thing, like this. For an open pipe, sorry, for a closed pipe that's open at one end, closed at the other end. This is going to give us, when a full wavelength goes like this, in which we represent in a standing wave like so, we're actually only getting 1/4 of the wavelength in there. So L in this case equals 1/4 the wavelength of the actual wave. So if L is 2.60 meters, we're trying to calculate the length. The length of the wavelength is 2.60 meters, so we can substitute 2.60 into this and calculate L, which will be 2.60 divided by 4. Cruising down to the next question. B, air is driven against a sharp lip, producing oscillations in the air with a range of frequencies. That's kind of an irrelevant sentence, so don't get lost in all the technical details there. Here's the key. Explain why not all frequencies produce standing waves in the pipe. Well, the obvious answer is the length only corresponds to fundamental wavelengths that will fit 1/4 of that wavelength into that length. You won't get a wavelength that would have naturally an antinode somewhere here because the waveform will collapse. You can only have a standing wave where in this case with the closed pipe, where 1/4 of the wavelength will fit nicely into that antinode node position. Okay, and that's when we're just talking about the frequencies produced in that pipe for the fundamental. That's not all frequencies will produce standing waves in the pipe. You will get other standing waves, for instance, with the wavelength of half that wavelength, so a half, that will fit 3/4, there we go, of the wave into there. So where L now equals 3/4 the wavelength. So this is an odd number of half wavelengths where that will fit in with the wavelength. Okay, you get the idea. They have to match the wavelength or the frequency to the length of the pipe. Okay, you can get more specific detail on the marking schedule for this as well, but that just gives you the general perspective. C, the sea organ contains organ pipes of several different lengths. Explain why differences in length of the organ pipe affects the sounds that are heard. Once again, only certain frequencies will be supported according, or supported by each length according to what wavelength can fit, and the fundamental wavelength determines the pitch of the note that is heard. It has any overtones that will affect the timbre, and the sound quality, or quality is a different word, so maybe we shouldn't use that, but you get the sense of it again as well. So different lengths will support different frequencies because of the position of antinodes and nodes and the distance between them, and therefore will support different wavelengths and a corresponding frequency. D, the speed of sound in cold air is slower than in warm air. So just take a moment to get that. So when it's colder, the speed of sound, so when the temperature drops, when it's colder, the speed of sound is slower, also drops, than if it is in warm air. This is for colder. I'm using the because it says it's slower than. Okay. Calculate the difference between the third harmonic frequency heard in summer and the third harmonic frequency heard in winter. Now, with a closed pipe like this, you're going to get an antinode and a node, and for the third harmonic it's going to have in between another antinode and a node. So we're going to have these positions for, we should sketch that. I've drawn that horribly once again. Oops. So let's just go over the top so it's really clear. So we've got 3/4 of the wavelength in that length. And we've got two speed of sounds. So from V equals F lambda, the speed of sound changes up or down. The wavelength over here stays the same because it's governed by the length of the pipe, which doesn't change. So the speed of sound is going to affect the frequency. If the speed goes up, the frequency goes up. If the speed goes down, the frequency goes down as well. So that's just getting general background perspective, making sure we understand what's going on. Calculate the difference between the third harmonic frequency heard in summer and the third harmonic frequency heard in winter. So we're looking at the two different frequencies. So we can say frequency summer versus frequency winter. And we've got the length, I think we calculated the length above. But if we, what could we do if we didn't? No, we did calculate it above. Let's just go and have a look. There we go, was to calculate the length. Calculate the length of the pipe, and we worked out that was 2.60 divided by 4, because it's for the fundamental. Okay, carrying on. I had a train go by, so I paused. So we're taking that length, 2.60 divided by 4, so same length of pipe, and I'm assuming we can use that. Although C says the C organ contains pipes of several different lengths, let's just scroll down. I think we have to assume that length of pipe, otherwise we can't calculate a wavelength. So assuming L from question A, so then we can use our knowledge here. If we know L, we can then calculate the wavelength. Once we have the wavelength, and we already have the speed of sound for both of them, we can rearrange for the frequency. So it's going to be F equals V over lambda, and we're just going to keep the same wavelength, but remember we have to recalculate the wavelength because it's 3/4. So same wavelength for both, two different V values, two different F values, and then we can compare the two. So let's calculate the difference between them. So you would have to do the larger minus the smaller. So if the speed of sound in cold air is slower, so for a lower velocity we're going to have a lower frequency, So it's slower in winter. So it's going to be a lower frequency in winter, so it's going to be summer minus winter. Anyway, you can do that calculation and find out what that gives you, and that's the end of question 1.